Okay, I prepared a few slides, mostly pictures, and I want to start with phase diagrams like this, where these are explicit calculation. I have a Hamiltonian, a parameter m, and disorder on the horizontal, and you see this kind of diagrams where below over here, I hope you see my cursor, is a map of the Anderson localization length, and on the top you see a map of one of these pairings. Nigel explained in his first talk, and you see that quantization mu equals 0 and 1 happens all the way to the boundary where I mean exactly the change is exactly where the localization length diverges. In fact, I'll use a very simple model to show you how spectacular this one is, and why, in fact, these topological insulator, topological phases are more interesting than just having integer or quantized response functions. For example, if I have this model is a model with chiral symmetry, and I put random fluctuations in both of the hopping parameters here. There is an mx and a tx. They are generated with via a random process. And if you try to calculate the eigenvalues exactly at 0 energy, it turns out you can do. And just to move. So I have to move this one again. So they take the eigenvalue exactly at 0, the eigenvector exactly at 0 takes the form of a product. And in fact, when you calculate the Lyapunov exponent, it comes in an analytic form, which takes like an average over the random variable. And you can do something more. You can take a typical example of white noise, then the localization length comes in this form, or the Lyapunov exponent come in this way. And then you will find, very interestingly, a manifold of 0 Lyapunov exponents. And these happen, in fact, at really large, actually as large as you want, random fluctuations in the coefficients. Now you can be sure that at these levels of randomness, there is no gap left. So the question is, why is this manifold coming out? So all of a sudden, at this huge random value, so just to give you a for orientation, these numbers here means W10 means we have 10, the fluctuations are 10 times larger than the average of the hopping coefficients, yet you have this metallic phase which shows up. And this is what, in fact, is interesting for the experimentalists. The why is this manifold coming out? And when you plot the topological invariant for this particular system, you see that you have this transition between quantized value exactly where this manifold, which was calculated analytically, happened. So the problem actually is a little bit reverse, at least in my point of view, and I know for sure also from the experimentalist point of view, is can you guarantee me that you have two phases here, and then they are separated by a true sort of thermodynamic phase transition where a measurable quantity diverges? And it turns out that the methods that Hermann described, model, of course, through after the Jean's work, and actually the Jean's and Hermann common work, supply the only route known to now today for an explanation of why this manifold of zero energy state, of zero Lyapunov coefficient emerges. And I can go on. In fact, that's my plan. You can look in other classes from the classification table, and the situation is the same. Whenever you see a change in the first, you observe the emergence of these metallic phases at these huge values of random potentials. It happens, so this was the A3 class and BDI class over here. This will be the A class. You will again observe that there is a manifold of a metallic phase in the phase diagram consisting of Fermi level and disorder strength. And you will find again that if you calculate the strong topological invariant, it takes quantized values with a not so abrupt change while crossing this phase boundary. But nevertheless, as you take your system larger and larger, you observe the single parameter scaling predicted by critical quantum transitions, and you can be quite confident that there is a critical point somewhere around. I should also mention that these actually are observed, at least for the anomalous Hall effect, has been observed and quantified extremely precise by the experiment. So here you see Hall, this is direct resistivity, diagonal, the off-diagonal resistivity, and different temperatures from 700 millikelvin all the way to 50 millikelvin. We see the off-diagonal flattening while the direct resistivity going down. And then if you apply the, you look at the scaling of all these quantities, you can detect a critical point. Therefore, there is a transition, a true transition with a critical point between the phase with the Hall conductance 1 and Hall conductance 0. And as you can see here, if you compare these two panels, here it's experiment, here is prediction from models. They match quite well, and it leaves no question that indeed the phases with different quantized transport coefficients are different phases of matter in the thermodynamic sense. Interesting to mention, none of these, so this is 2014, so the anomalous Hall effect samples were perfected in 2013. Quantum spin Hall and the TRS stabilized topological insulators have been around since 2007, 2008. However, no such evidence for such a critical point has been found in experiments. Just to show again why the regime of strong disorder is remarkable, if you take Hofstadter Hamiltonian, here is the spectrum mapped by magnetic flux, Fermi energy. It has a lot of gaps, as it was mentioned many times. When you add disorder to the system, most of these gaps washed away, and in fact, you only, at some point, you will see no gap. The statement about quantum Hall effect is that somewhere here in the middle of this spectrum, there is a fine line, and Hall conductance, in fact, is quantized all the way to that fine line where it changes abruptly. The existence of this fine line, including the scaling near this phase transition, in fact, is the subject of 99% of the research on quantum Hall effect or integer quantum Hall effect. Same transition can be found, for example, in amorphous system under magnetic field. Simulation showing A3 class in 3 dimensions. We see again the same phenomena. So the bottom line, we also see the same phenomena for spin Hall. The bottom line is what this table is about. So in each class, in fact, the examples that I show cover quite a number of classes from this table. As you can see, is not K theory. If we were going by the K groups, then we should have seen other groups around here. In fact, the table is very simple, and the table is precisely about these phases, which in fact are separated from one another by such a Anderson localization-delocalization transition. Therefore, they are truly distinct phases in a thermodynamic sense. You can go in the lab and you can distinguish them. And what is missing from this picture are the weak topological invariants, where if you change the quantized value of those invariants, you will in fact you can do that. You have to close the gap, but you will not cross a topological. You will not cross an Anderson localization-delocalization transition unless the disorder is a little bit engineered or of special cases. We also heard about Bull boundary correspondence in the spectral formulation. In the spectral formulation is that the Bull gap is filled entirely by boundary spectrum. However, if you go to the experimentalist, that's not quite a useful statement. In fact, what experimentalists will be interested in, if this boundary spectrum is in fact delocalized, which means the wave functions are delocalized along the boundary. And Hermann mentioned today that, again, the methods which rely on pairings between K-theory, cyclic homology, pushed all the way into the Sobolev spaces, gives you these results. So going back to this system, I should say that everything that you see in Z2, such statements are missing. At least this is what I know. So even at a single particle level, we still have missing pieces regarding the strong disorder. As Hermann mentioned, such results only hold in when the level of disorder in the bulk is weak. And we can have strong disorder on the boundary. And now the slide I have about fractional quantum Hall effect. Of course, after beefing up the magnetic fields and more pure samples, people start observing not just integer plateaus, but rather plateaus which are aligned with the fractional values. And the situation is quite similar. We have a quantized off-diagonal transport coefficients, while the direct transport coefficients go to 0, indicating insulating phases. It was for a long time unknown from the experimental point of view if in the fractional Hall effect we do cross a critical point or not. And it is only recently where such scaling analysis, that is pure enough samples, good values of magnetic field, and then as you cool down the sample, you start seeing again that all these curves in fact satisfy a single scaling, the prediction of the one parameter scaling, with critical points appearing clearly in these diagrams. So the reality is that we have no explanation for the emergence of these critical points. I then would like to maybe finish with a slide. Maybe let me Google integer quantum Hall effect. We'll find it in Wikipedia. And I want to talk about this highly misleading applet. So this editor considered the Landau Hamiltonian. I have a picture here. And then here, in this applet, he, as you can see, he increases the magnetic field. So this line is the magnetic field, and he calculates the Hall conductivity using Kubo formula, and he gets these very nice plateaus. Now, if this author would have had the decency to actually check how the experiments are done, he will find that they are not at all as he imagines. As you can see in this picture, the Fermi energy is Hall fixed. We have no access to this quantity experimentally. What is Hall fixed in these experiments is the electron density. So if you put on this axis the electron density, then you'll find, quite contrary to what is depicted here, just a straight line. I wish I could stop it. You'll just find a straight line if you replace this axis, if you still modify the B field, but you maintain not the Fermi energy, but the electron density. Therefore, you'll scratch your head and you'll see that the explanation of these plateaus is not as simple. And unfortunately, this kind of misunderstanding about, and in fact, just a look at how the experiments are carried would have helped, putting the right information and not misleading the young generation, thinking that the explanation is so simple as imagined here. Then, like Herman mentioned, and then I'll stop with my introduction, is that if you look you can do the experiments varying the magnetic field, or you fix the magnetic field and vary the electron density. You are in a situation where you have on this axis, you have a top pairing, and on this bottom, you have a lower pairing, and one of them takes quantized values while the other one takes a continuum value. Certainly that cannot happen if you are inside a C-star algebra. And as he explained, the only way you can explain this kind of phenomena where the purpose is explaining the plateaus. Why is this plateau here? Not the integer values. Why is the plateau here? If you can explain the existence of plateau, you will also be able to demonstrate that there is a critical point between this phase and this phase. Then you have to exit the C-star algebra, and you have to be somewhere in between the C-star algebra and its weak closure. And Hermann identified Jean and Hermann identify these Sobolev spaces to be the right, in fact, the optimal spaces. So the question now is, of course, what I will now turn to the sort of set the tone for the discussion is, we learn several topological invariants, which we can associate to strongly correlated phases. They can be numerical. They can take form of these tensor categories. Now the question is, how do we distinguish if they are strong or weak? In other words, if we know if it is to change these topological invariants, we have to close the gap. But a deeper question is, do we have to cross an Anderson localization and delocalization transition, and therefore see critical points like here, or we just go smoothly from one phase to another? So that's my that's my introduction, and we'll see if where the discussion goes. So I'll then open the floor for discussions.
So for the time reversal invariant topological insulators, what is the experimental status with regards to the question you're asking about the transitions? So I as far as I can tell, I don't think there's something there, right? So I'm not sure, I might be mistaken.
So they are results, but if you look careful over the result, the experimental results, they in fact demonstrate quite the opposite, that there is no critical point.
Right. So it's a weaker phenomenon than what you're trying to explain to us.
So I'm not sure if that's due to difficulty in sample preparation, which is a little bit special, but that's certainly the status.
Were you asking about the general time reversal invariant, or with odd time reversal invariant?
So I think A2 in 3 dimensions.
The odd, I think the terminology is
okay.
odd. Yeah.
Mm-hmm.
Yeah.
So Emil, you say there is no delocalization transition.
So yeah, us in the numerics, we see clear signature of this Anderson localization transition. So in numerics, I think we've seen them beyond us and others. We've seen this transition. I'm not sure why the experiment has difficulties in confirming this. And certainly there are the other puzzles, the fact that the quantum spin Hall samples, you put them in magnetic fields as high as 1 Tesla, they still show ballistic transport on the edges. This has been confirmed with mercury telluride quantum wells and with gallium arsenide quantum wells. There is another puzzle why the localization length of quantum spin Hall samples also seem to be quite small, actually insignificant with the anomalous quantum Hall effect sample. The process to generate anomalous quantum Hall samples is much more difficult than the other process. Yet in one case we see all the traits of the topological phase, and we don't see in the other. I'll ask a question. In fact, it's addressed to Nigel. So Nigel, we were discussing, and Nigel heard me many times saying pushing into the Sobolev, and you said, I don't understand exactly what it means, but I think it's very natural, isn't it? Even if you work with manifolds to try to push these invariants into a Sobolev space rather than C infinity or something.
Yeah, it's a natural thing to think of, and I guess there are some interesting conjectures about the homotopy type of Sobolev maps satisfying just some Sobolev finiteness condition rather than smoothness. You have two manifolds and you look at all possible maps from one to another of some fixed Sobolev type. What is the homotopy type of that space? My impression is it's just extremely difficult to, in general, prove anything. There's some beautiful conjectures that I learned from Shmuel Weinberger, but I don't know if he was able to prove anything. Even he was able to prove anything. So in short, we, the mathematicians, have thought about this. There are some limited numbers of results which I can probably find and put in the chat concerning maps between spheres, but I'm not sure there's much beyond that. But let me.
Is this what you want, Emil, or do you rather want something like cyclic cocycles and so on, churn theory in that setting?
Yes, but I will guess they are related, isn't it?
I would guess the same. Yeah. Let me see if I can find something and then get back to you.
So in a discussion with Alain Cohn, he foresee this possibility of going in Sobolev precisely because some or most of the terms in his local index formula cancel out, precisely because we are working with flat spaces. And he, I think, was ready to bet that if we go outside that setting and other terms in the local index formula show up, we should not be able to push these calculations into Sobolev.
I think John had a question or comment at some point.
Do you hear me?
Yes, very well.
Okay. I don't know about the situation in topological insulator because I didn't follow the topic. But in the case of the quantum Hall effect, the integer quantum Hall effect, these critical points arise because a change of Chern number implies that automatically between the two plateaus, there is a divergence of the localization length. The localization length can be defined algebraically by using the Sobolev space, and then for the Fermi projection in particular. And so if you change the projection, if you look at this expression as a function of the projection, you can prove that indeed you can define a measure which is absolutely continuous with respect to the density of states. And this measure is the rigorous way of defining localization length. Now, this measure is also associated with the correlation measure for the current correlation measure. And you know perfectly well, Emil, that we checked together that these critical points are associated with the singularity in this current correlation measure. Okay. Now, whether this is the general phenomenon or not, I don't know. I'm talking about the bulk. I'm not talking about the boundary, because in the boundary there is something new that happens, namely because you have the zero modes on the boundary. The zero modes are special and are not localized in general. Okay? But these zero modes are really a boundary effect. They are not nothing to do with the bulk. So if you pass from one plateau to the next, you are expecting that the localization length is diverging, okay, in one way or another. That's actually is the reason why the fractional quantum Welle effect is possible, because they occur precisely when you have a transition from one integer to the next integer. And so in this case, the effect of the disorder doesn't play any role. And so the electrons now are not screened by the disorder. Therefore, they are interacting through the Coulomb potential, and they create this pseudo particle that we call NEN. Okay, which also behave at the lowest possible approximation. They look like behaving like quasi-particle with fractional charge, essentially. And so you can again apply the scheme of the integer quantum Welle effect for this particle, and because the charge becomes fractional, then you get fractional quantization of the conductance for that. But this is just a scheme; it's not rigorously proved. Okay, but this is the way physical intuition is guiding us. And so, again, there is no reason why the localization length of this quasi-particle should not diverge between two fractional plateaus. Okay.
So, okay, the title of the discussion is Rho algebra, Groupoid-algebras. For this, in this context, so I know Bram and Chris, they work on index theorem for the in the groupoid setting, and the groupoid setting is precisely Jean and Johannes groupoid algebra, which comes canonically associated with any pattern. And Ralph has his work on Rho algebras, and and Joske also. Joske was I saw his presentation in 2015 when he put topological insulators in this context. So maybe I'll start with the Rho algebras and ask Ralph and Joske if there is any, how do you see the picture? Is there a way to go beyond the gap condition and so on and so on.
Well, I think that the best thing that I know is exactly what Hermann explained also in his talk, and which is going back to these old papers, namely you try to write down this Chern character and you hope that that still works. There you would need some kind of maybe Sobolev-like estimates, and if you are lucky, then and you can show that the Chern characters make sense, then they would still give you integer values, presumably, and then you would be in a case when you can say something. But I don't see any way to turn this into a K-theory of some algebra, unfortunately.
The ergodicity plays a good central role in these approaches. Ergodicity can be formulated in the context of coarse geometry.
Well, I have never seen it like in this context, no. You don't look at a specific group action, you take some big universal thing like the Stone-Čech compactification, and you don't expect this to be ergodic, you expect it to be big and kind of universal, so in some sense the biggest possible thing. So you wouldn't expect ergodicity in that context.
I mean, I think that is a kind of important difference between the cross product and uniform or non-uniform row algebra picture, is that the cross product is really just about one specific Hamiltonian often, or okay, it's family. Whereas the row algebras are in some sense a bit more useful for classification because they're now talking about a universal construction which allows to pass between potentially different or a large class of different models. So in that sense, probing the spectral properties of a single Hamiltonian is probably going to be more difficult there, but I don't know for sure.
Yeah, so my interpretation of the difference is that with these cross products, you carefully specify which kind of disorder you allow, whereas in the row C-star algebras, you try not to specify that, but just allow all kinds of disorder without any, so you only impose the minimal requirements that Hamiltonians should kind of be local in some sense, to have at least approximately finite propagation, and then that's all you put in, nothing else.
But in Bram, so what's the situation with the groupoid?
In what sense? I think this was more or less addressed now, right? That you fix a specific lattice, look at one transversal, and you compute from there. I think when we were in this meeting in Mexico, I had a brief conversation with Ralph, and there should be some map maybe from, or I mean, could one make, this is something I don't understand at the moment. It's like, how would you relate the row algebra to some specific groupoid algebra? Like, would there be a map from one to the other, or something like that?
I think there should be a map, yes.
I believe the transversal groupoid, the C-star algebra, the transversal groupoid sits within the uniform row
That's
algebra.
what I also think, yes, it should sit inside.
Yeah, I think Yosuke proved that at some point.
And the only thing you would need is to find a position operator or something like that in your C-star algebra. Once you have a position operator, you get a or position operators, rather, if you have more than one dimension, then you would get a representation of functions on Rn that would create a row C-star algebra. Then, the C-star algebra that you are interested in should be contained in that, because it interacts well with this position operator in a mild way.
Right, but is this containment somehow canonical, or could you find different copies of that thing?
Well, what do you mean by canonical? So
Well,
if you have an idea what position means, then I think it might be canonical.
let me phrase it. Is there a preferred way to realize it inside there, or are there different ways to do that? And maybe they're all good enough if you want to compute some invariant. But
well, for some purposes, even in very standard examples like the SSH model, there is this, well, Groupoid-algebras already noticed that the, well, which element of K1 in that case is the trivial phase depends on, well, a choice. If you look at the SSH model, then you have to, well, in the model, you pick the unit cell. And depending on whether you say that unit cell is something like an AB or a BA, so you have two types of atoms, and you could put an A or a B atom on the boundary. And depending on which one you put, one of the two phases would be the trivial, the other one would be non-trivial. And somehow this this explains that there is some kind of choice of what the half space is, which looks very, very strange to me, not canonical at all. I'm not sure whether this could happen in, well, in the bulk as well. I think in the bulk it should be less, if the coordinate shouldn't be so important, but if you look at the half space, and there seems to be some interesting choices there.
right.
So in this context, I was also wondering whether we miss something by just looking at algebras. Because this choice in the SSH model, it's somehow uncomfortable.
So what will be an alternative?
I can say something about this choice. Actually, if you try to look at the continuum version of the SSH model, so this really is the Jacques-Rabbi Dirac Hamiltonian. Then you would find that you get a zero mode, a localized zero mode on the half line, depending on the choice of boundary condition. And you can see that this choice of boundary condition, in order for it to be chiral and self-adjoint for this half line Dirac Hamiltonian, you need to impose some a Dirichlet condition either in one of the two chiral components. This exactly corresponds to the choice of cutting the unit cell in the for the half space SSH model. So actually, this ambiguity is not really a problem. And
sorry, can you just say that again?
Yeah.
What corresponds to this choice exactly?
The choice of self-adjoint boundary condition. So if you take the Dirac operator, the chiral one, so it's sort of a d by dx in one corner and minus d by dx in the other corner. So the sort of classic Dirac operator that's chiral. Then the self-adjoint boundary conditions on the half line, you've got some choices, but they invariably involve either a Dirichlet condition on one component and no condition on the other, or you swap the rows of these chiral conditions. So already there, the choice of boundary condition determines the index of the resulting the operator. And in fact, there's an index theorem. You could call it the Wiener-Hopf index theorem actually for this sort of operators. And that the role of the boundary condition is quite important. So already in the continuum model, this can be seen very explicitly. And in the lattice model, which the SSH model essentially is supposed to be an approximation. You also have the same condition, and what this the choice of chiral component in which you impose the Dirichlet condition is exactly the choice of termination of either the A sublattice or B sublattice at the boundary. Does this make some sense? Yeah.
So you have,
sorry, if I had a board, it would be easier to explain this. But, yeah.
But I think that it might be clearer in the simpler tight binding case. So in that case, you have to just think about these dimerized limits. You know, in the SSH model, you have this chain of atoms of the types A, B, and there is kind of, well, for the interaction, there is two kind of degenerate cases when they just interact as pairs, and then these pairs don't talk to each other. And you could have an AB-AB pair combination, or you could have a BA-BA pair combination. These are the two, well, kind of the two most obvious different, Hamiltonians for this system. And now, depending on whether you have which half space you choose, whether you have a B or an A as your boundary atom, there would be one atom left over on the boundary or not. And if one is left over, then there would be this special boundary state, and if not, it wouldn't be there. And of course, the trivial phase should be the one where there is no special boundary state, and the other one should be non-trivial. So you see that the non-trivial, or the trivial topological phase depends on which half space you choose. So the boundary map depends on the choice of the extension. If you choose a different extension by picking a different half space, then you might get a different boundary map, and then it could be that a class which looks, well, which has an invertible lift in one extension doesn't lift in the other extension. And in this SSH model, this is not just something bizarre which happens mathematically, but it's really visible. Well, so we can just choose the half space and see what happens easily to see this effect, which is a nice point, I think.
Right, but Ralph, the reason why I mentioned the continuum model is because over there, if you just consider the derivative operator on a half line, then the choice of boundary condition, whether you impose, the choice of boundary condition determines the index of that operator actually. So you take that operator plus some mass term which has some condition on its eigenvalues. There's an index theorem that tells you what this is, and if you want to cook up kind of a unitary symbol in some symbol space, it actually depends on the choice of boundary condition. So it's not intrinsic to the formal differential operator on the entire space, but also in the boundary condition that you want to impose subsequently. So in order to get this continuum about H correspondence, which is really encoded in a rather old index theorem, actually. I think I have a reference for it. It's by Goldberg, one of his textbooks, GOHBERG, for these derivative operators on a half line. So the upshot is there is no intrinsic notion of the bulk topological invariant for these chiral symmetric Hamiltonians, unless you have a preferred choice of unit cell, and the preferred choice of unit cell in the continuum picture is analogous to the choice of self-adjoint boundary condition you will impose at the boundary. So that's roughly the picture. So there's a consistency check in terms of the ideas.
So I want to point out maybe somebody more qualified will be able to tell me. I was watching this talk from the global NCG assembly maps, discrete group, and index theory, and it looks like here, for the first time, I will guess, there are index theorems in context different from what we are used to. So if anybody check this, I was trying to browse and find where is exactly the local index formula, but in any case, it's of course every time when we see an an explicit local index formula, it's a great news, which we should try to take advantage of. And it's quite interesting how Baum enters in all this picture. In fact, when I explained to Richard our geometric identities, how we get this index stuff pushed into the Sobolev, he immediately said, well, that's Baum. So Nigel, how does that enter in all this index theory? And
I'm not sure what the connection is between this idea of extending to Sobolev spaces and Baum-Kohn.
But in index,
what you're showing me on the slide looks very familiar to me. I'm very happy with everything that's on that slide. It makes perfect sense. So,
here the group is
but it doesn't.
discrete,
I don't understand how it connects with what we're discussing.
But
Well,
here
a
the
possible-
group is discrete, Emil. We would need something with a non-abelian continuous group, so Lie group. There, I would like to see how to construct the Chern characters and so on.
for example, point symmetries are really relevant. Why not? We don't
So
know.
a point that Richard might have it in mind is whether you can to what extent you can factor this map through the K-theory of this reduced C-star algebra. Here, this map is constructed on the domain of the Baum-Kohn assembly map. And if you want to write it down on the group C-star algebra, well, if you know the Baum-Kohn conjecture, of course, it doesn't make a difference. But if you want to prove something about it, well, there have been various papers that try to do this by writing down some kind of cyclic co-cycles that make sense on bigger subalgebras of the group C-star algebra than just the group ring. So on the
But
group
Ralph,
ring, everything
this is all
right.
subalgebras of the C-star algebra, not bigger things than the C-star algebra.
Well, that's true. But these subalgebras also remind me of some kind of, well, maybe they're still Sobolev spaces of the smoother type. So like the Schwarz algebra, things like that. But in some of these papers, like Michael Pushnik, it's something with traces on the L1 algebra. So the group L1 algebra is kind of more amenable to writing down explicit co-cycles because you can check boundedness rather easily by L1 norms. You just need a bounded co-cycle, something like that. Then the question is, would this somehow define a map on the K-theory of the reduced cross product? And these are the kind of difficult questions in this connection. But Nigel is right that this is more like subalgebras of continuous functions where you want to make sense of some pairings without having full smoothness, or even in a context where you can't talk about smoothness so much because you have non-abelian groups and don't really have a nice Schwarz algebra. So if you are on the boundary of knowledge of Baum-Kohn, you have very wild groups where you don't know much about their behavior. The groups that you care about are so nice that, well, we probably have nice smooth subalgebras in them and wouldn't have to worry about these more advanced techniques.
But am I correct that this, for example, this statement here covers the space groups, the discrete?
Yeah. For groups of motions of Rn, groups of motions of hyperbolic space. These are examples of groups where we understand how to solve these problems that Ralph is referring to. We have good subalgebras which carry all of the K-theory. So if your group gamma acts is something like a Bieberbach group, it acts on Rn isometrically and properly, then for sure everything is fine. This map does factor through the reduced C-star algebra.
However, to produce local index formulas, it's another step, I'll say.
That's true, but I'm guessing that's also mostly done.
I think that this has been done for a while now, right? Like if you think of the Kolmoscovici paper from '89, I think, on hyperbolic groups, there's a local index formula there, isn't? Or am I misremembering?
Oh,
That's correct. I think more relevant to this particular context would be work that Han Wang did in her thesis under Gennady, under Kasparov.
Right, that's true.
So that's from the, I don't know, 2000s, 2010, something like that.
And I think this old work was about kind of group cohomology only. So it was localized at the unit element. Whereas I think from what I've seen in some of the slides, the point of this talk was that he can do something also for, well, for periodic cyclic co-cycles on the group algebra that are not living at the unit element.
Okay.
what else I want to point out? The talk by Joachim, I immediately could connect with that talk, because if you check the Sobolev norms that they give convex algebra in which multiplication is continuous, and so it's very interesting, because then he said even defining K groups in this setting works. So do you remember the talk?
I mean, Kuntz and Andreas Thom have made some progress, right, in notions of K-theory and index pairings, and maybe even Chern characters for just locally convex algebras. But I don't know how computable a lot of these things are.
Well, I showed him this example that I just showed in the first slide. I said, let's say this example and treat it with his method. And he said, yeah, you don't need to go all the way to pairing. In fact, this can be seen as K. So you don't need pairing, but rather stay at a K theory level for this convex algebra.
But I think that these algebras you want are not really locally convex. So in these results, there is this intersection of LP spaces, or they're locally convex algebras, but they are not. They're beyond what K theory is normally studied for. Topological K theory is defined for Fréchet algebras, but the definition of Fréchet algebra in that context includes submultiplicative seminorms defining the topology.
Yeah.
And this LP norm intersection is the standard counterexample of an algebra that is not of this type.
So it is if you only take L infinity and the LP norm that Hermann had in his. So that's, you can check that it's submultiplicative.
L infinity is, but these LP norms are not, even on the diagonal operators inside or something.
But if you combine only L infinity with one of the other norms, that will become submultiplicative.
But then you no longer have projections in that algebra, I think, because, or you don't have continuous homotopies in that algebra, things like that. So the problem in these Anderson.
Right, that's right. So the continuity in our index theorem, it's only with it's not with respect to L infinity part of the norm, but only with the other part. So that ensures the stability of the index.
Yeah, but if you want to explain that the index, let's say, doesn't change when you move the Fermi energy a bit or something, if you have some very obvious kind of homotopies that shouldn't change the Fermi energy, if you move it inside this Anderson, this mobility gap, for instance, then it should stay constant. And
no, it doesn't stay constant. I mean, you're right. I didn't claim that. I just said it stays constant under norm-continuous paths of projections, which one does not have in the applications here.
Yeah,
in the bulk, the theorem states if you vary the Fermi energy and you assume continuity only not under the L infinity part of the norm, but rather the rest of the Sobolev term.
Yeah, the strong invariants, of course, stay constant, but not the other cyclic pairings. Okay, not those which are not integer valued.
Yeah, but then if they don't stay constant, so they could just jump. I mean, or you say they are continuous, so they wouldn't give you integer values. And somehow this, well, this doesn't sound very K-theoretic to me. So,
Doesn't sound very what?
It doesn't sound very much like K-theory to me. Well, of course, if you have a von Neumann algebra, K0 could be just real numbers. That happens
That's
sometimes.
right. It's a huge algebra that you have. It's okay. In particular, yeah, the image under pairings is the real numbers.
I understand what Ralph is.
But nevertheless, I mean, you do have the boundary correspondence. That's what's surviving.
Yeah, I understand what Ralph is saying. If you try to explain these results in pure K-theoretic setting, even with these convex algebras, then you cannot avoid, I mean, you cannot exclude the L infinity part. That will be part, in fact, of the definition of the K-theory of that algebra. So you cannot exclude that part. So so then I understand the objection that indeed you cannot explain the quantization of the top pairing just from the K-theory.
Yeah, so one could, of course, try to push topological K-theory beyond what's done before and go to these intersections of LPs. But this seems hard because very basic things are not true anymore, like, well, invertibles are not open. Well, so it's difficult to do anything in this class. So maybe you have to do something like algebraic K-theory and see how well it works. I never tried this seriously because I think it would be very difficult to do. And then I'm wondering whether it's really worthwhile to do it. If you can prove things using the pairings and not on the K-theory level.
I mean, this is a somewhat unrelated question, but kind of related. So let me ask if, we've been discussing the cyclic pairings, but I mean, there's still this issue that was pointed out that we don't yet understand torsion invariance very well in the strong disorder regime. And at least as far as I can tell, these Bezos spaces or Sobolev spaces are not really going to, well, or maybe Herman or Tom can answer better, but as far as I can tell, the techniques that come into this Bezos theory are not exactly, I mean, because it's mostly just an analysis problem to define these indices in the mobility gap, but I mean, these Bezos spaces are built from traces.
Yeah, but I disagree with the fact that we don't know anything about the bulk invariance in about Z2 valued bulk invariance in the mobility gap regime, because that we do know. We can push the definition. I mean, it's just the same theory. I mean, you
can define them, but as far as I am aware, I don't think there's been a result.
Almost surely the same also, so you get almost sure values.
Yeah, I agree. You get almost surely the same, but when you move within a mobility gap, as far at least I'm not aware of any result that says that this Z-mod 2 stays the same.
Okay, maybe we didn't analyze that in detail, but I'm almost sure that it's the same.
Well, I mean, at the very least, the proof of it in the complex invariance is not going to work. Well, the proof that one does in that case. Because yeah, I agree. You can define them because it's just if you have an ergodic measure, and that will be almost surely constant. But if you then consider a deformation within the Sobolev algebra or something like that.
Right. We didn't do that. Okay.
Yeah, so you need you need two parts, both parts of the index theorem, one which gives you the discrete range or the countable range, and the other one which gives you continuity.
Yeah, I mean, I don't know if Johannes knows a little bit about this, but well, I don't know if anyone else does either. But you know, in the scattering theory literature, where people look at half-bound states and Levinson type theorems, and they try to link to things like the spectral shift function and spectral flow and the Witten index, which are in theory defined sort of outside of a general Fredholm setting, but you know, somehow still kind of close, and it still has some of those properties there. I don't know if maybe some of these techniques are also useful here as well, where okay, if we can try and think of certain indices as spectral flow or something like that, then if you then translate that into like the spectral shift function or something similar, then that's going to be well defined in a larger setting, but I don't know if that's relevant here or not.
So, I mean, one thing which is also not clear is, okay, I mean, Terry came up with these formulas to localize the Z2 indices, which is not at all an easy thing to do. And you get the Z2 interpretations also for these Z2 invariants, which are really local formulas for them. And that analysis also uses, or one way to analyze that and prove that uses spectral flow again, so Z2 valued spectral flow. But also that full analysis has not been pushed into the strongly disordered regime. So that's another open question there, where I don't know how to proceed. But Terry, I think, has seen that it works.
I think, Johannes, we in our paper on quasi-crystals, you had an interesting remark that when you define, let's say, a winding number going along the loop, you can have piecewise continuous loops as long as, when viewed from an angle, they give you some sort of a continuous. Can we, for example, push the winding number on when can we push the winding number on piecewise continuous loops, or when the differentiability can be only assumed piecewise?
In principle, it's defined even for continuous. I mean, for piecewise, you want to have a jump.
So it should be a jump in the function, but not in the derivative.
Can you draw a picture?
Wait. I can show you with my hand. So if I look at a circle, then I take a sector and I blow it up, so that when I'm looking from the center, I always see a loop.
Mm-hmm.
In the same way, if you can define topological invariants which are fully rest on the continuity, on the first derivative of the function, and then if you have a function which has a step, yet the left and right derivation coincide, you'll have no problem in defining such an invariant.
And you would like this property for what? To be to get out of the continuous category, or
That's right.
as algebras.
Yes.
Maybe another question, which is again a little bit unrelated, but we were discussing before about one of the, well, maybe not the only reason, but one of the reasons things work well for these cross-product pictures is that you know, the Kohn-Moscovici cocycle, you know, only the top term remains. So your Chern character is computed by just the Hochschild class, or just the top level term. But I mean,
can I ask you why you always mention cross products and not the groupoid?
So I mean, it works with the groupoid as well, because that's,
yeah.
And the groupoid is equivalent to the cross product by R, so it's the same thing there. Yeah, I mean, if you have these cases with some curvature or where lower order terms appear, I mean, okay, I mean, maybe some element, well, I guess I don't necessarily see the link to spectral theory, but I also don't necessarily think that this is a bad thing to happen, that you would have some example with a defect or something like that, where maybe a lower order term from the local index formula contributes. I think that would be interesting, actually, but I mean, it's a separate question to robustness under spectral questions.
Not sure. Yosuke, are you here? Are you there?
Sorry,
yes.
Can you tell us about your higher index theorems?
Sorry, which one? Sorry.
Yeah, in this new work you have on defects, lattice defects, you mentioned that they are based on one of your recent work, which was on
yes. Let's see. Recently, I was working in some index theorem, a higher index theorem manifold, and it's co-dimension 2 submanifold. If one have a manifold and which have a nice co-dimension 2 submanifold, then the non-vanishing of this co-dimension 2 submanifold implies non-vanishing of the index of the original manifold M. So this is an answer to some problem raised from Tomaszek in 5 years ago or so, around that. And so this is a problem in geometry, and so solve some question, answers to some question in positive scalar curvature metrics. But the simplest case of this problem is that case that the manifold, larger manifold is the 2-dimensional torus, and the smaller manifold is a point. This is the simplest example which we can apply the theory. And this case corresponds to the by Fourier transform. In this case corresponds to the study of some 3-dimensional lattice with discrete dislocation. So how I want to explain how they are related, and
yeah, I saw it. You had these huge diagrams.
Yeah. And so the proof of the origin, our high index, so our construction of the morphism between the K group of group C star algebras is given by certain extension of group C star algebras of the fundamental groups. So 0 to the fundamental group of smallest manifold and some shift algebra to the group shift algebra of the fundamental group of a large manifold to 0. This we can construct this kind of group, extension of shift algebras. And in our simplest case, this corresponds to 0 to C star. Oh, sorry, we need to take a suspension of the at the ideal 0 to C C0R tensor K to some shift algebra to C star Z2 to 0. This kind of short exact sequence we obtain. And this is nothing but short exact sequence of operators on three-dimensional lattices with screw dislocations. The total shift algebra, it corresponds to the set of operators on lattices with screw dislocation. So in this way, we can relate the theory of some dislocated topological insulators with the study of geometry of manifolds. And the same proof works for determining the boundary map. We can use coarse geometry. In particular, we can use the coarse assembly map to determine the boundary map, because a boundary map of the K-homology group is easier to determine than that of shift algebra K theory, because we have boundary of Dirac is Dirac principle. So
Good sounds and
yeah. So I think how to say. So in this way, so geometric method is used to determine some mapping topological insulator. This is what we did. I did in my recent preprint.
Thank you. Nigel, I was looking over your old paper on manifolds with boundary, I guess. And the connection was through my reading of this cobordism thing. Do you see the relation clearly? And
this cobordism, what do you mean by this cobordism thing?
Well, this cobordism theory, I think it's a mathematical subject.
Yeah.
Well established. So is your work fit into that? Do you see how your work fit into that context?
I mean, I would say that the major problem in any type of bordism is to determine what the bordism groups are. In other words, determine what the spectrum is. And well, I suppose what I did shows, which is also what Attir and Singer did, shows that you can use index theory to determine some features of the bordism spectrum. So there's a connection. I wouldn't say it's. I wouldn't say anything that I did there goes beyond what Attir and Singer already knew. What I did was make a much more transparent proof of the theorem, which is due to them. It fits into the language of coarse geometry. So from that point of view, it's something that's maybe more accessible to application in physics context. But it's the theorem, the results are due to Attir and Singer.
Thank you. Okay, so there is unfortunately this discussion was scheduled a little bit earlier because tomorrow we'll have the talk on coarse geometry, and only Friday we have the talk on groupoid structures.
Emil, can you try to explain again what you were saying about winding numbers and curves with jumps of a certain carefully controlled type? I just want to see if I can absorb at least what the question is.
I remember that Eric Ackermans, he did some numerical calculations coming up in this problem with quasi-crystals with the Fibonacci model, where he had discrete results for something which corresponds to different finite approximations of the Fibonacci chain. So I don't know whether you are a little bit aware of this Fibonacci chain.
Sorry.
No.
But it's
that's I don't think that's the way to.
So the Fibonacci chain is a model where the potential depends on the Fibonacci sequence, and this is a sequence which you get by this famous substitution rule where you replace A by BA and B by A, and then you go on and you go on. I don't know whether I've seen something like this model.
Okay, I think I know roughly what you're talking about.
So then he doesn't do it up to infinity as we would do it to get an infinite chain, but he does it only for a finite number of times. And then he gets a finite chain which has a certain length. And then his idea was to there are then naturally, if I fix the step of the substitution, let's say it's the nth step of the substitution, that I get the nth Fibonacci number, many A's and B's, but there are partner chains which naturally are also in the same hull, and there are Fn many, and then he sort of associates to each of these chains a number which he then would like to compute. From this, he would like to compute a winding number. And so the problem is you have a discrete point set in C, which doesn't hit 0, which is somehow ordered. And then you want to define the winding number of this thing, which of course doesn't make sense. But in the limit where this procedure goes to infinity, you expect that this is the winding number of something continuous.
But let me point to the following. Let's look at this simplest pairing, which gives us the winding number. And now you want to estimate what is you have a unitary defined on a circle, you have unitary 1, unitary 2, and you try to estimate what is the difference between the pairings of these two U1, U2. If you look at thing, you will say that it will depend on both the continuity and the first derivative, but because the co-cycle, I mean, the cycle, it's a periodic co-cycle, it only depends on the derivation. So if you can bound it only by a derivation. So then it looks like you will be able to get away with let's say a U2, which is not necessarily continuous, but it's only have a continuous first derivative.
I don't understand why you don't need continuity for the cycle.
No, so you need continuity to make it finite, but then when you take the difference between the two such pairings, you will find that you can use the periodic cyclicity to actually only bound such a difference on derivations, on first order derivations. Because you, when it is to, for example, you use, you have a product. What's the inequality? You break the inequality on the terms inside the product, and naively you will say, oh, it depends on also on the difference between u1, u2, not only on the derivation, but the cyclic property enables you to move the derivative back and forth between the two terms in the product. At the end, the difference is only a function of the derivations.
So is this the same argument which says that you sort of need each of the two functions to possess half of a derivative instead of and nothing more? Is that what you're talking about? So if you write down the winding number and you take apply Fourier theory to it, then you see right away you just need each of the f and 1 over f to be in the 1/2 Sobolev space. Is that what we're talking about here?
Yeah, that's right.
Okay. And are there reasonable functions in the 1/2 Sobolev space, and for which this result gives a surprising answer? I don't know anything about the 1/2 Sobolev space. I don't know who lives in it.
Well, not in the smooth case, but in the non-commutative case where the co-cycle is coming from a circle action, then these are the pairings that Hermann mentioned. They all come this way, and they can be pushed to this half Sobolev space.
Okay, thank you.
So yeah, there is a difficulty somehow when you go back to the classical case, because in that case, if you look at the spectrum, because you are on when you map it as a function of the base space, you get continuum spectrum, and you cannot. There is no way to get pure point spectrum for this unitary. Not for this unitary. For what? So you need pure point spectrum of the Dirac operator, which you will cook up out of this unitary. So Johannes, you are still processing that, what I said?
Sorry?
Are you still processing what I said, or you are okay?
I'm processing. No, I don't really understand what you want. I don't really understand what you want.
No, it's just let's say a simple observation that indeed, if you try to bound the co-cycle or the cycle, you need all the parts of the Sobolev norm. But when you only look at differences, only the part which involves the derivative is needed.
Mm-hmm.
And nicely comes from this cyclic property of the cycle. So here, as you see, you need the A0 stuff, but in fact, you can shuffle this one around so that you put A0 at different places. So you'll get a derivative on A0 when you calculate such a difference.
I see. Mm-hmm.
So then this gives you, if you have a reference, let's say a reference input here, then you could easily get a bounded value by just requiring continuity on the derivation, not just on. So I know, Herman, you are processing, but take this difference and first you establish continuity with respect to A1 prime. Of course, in this factor, you still need A infinity, no question. Okay, so you still need A infinity. They go into this factor. However, in this part, you only need the derivations.
But then you apply these typically to the same A's, right?
That's right. That's what I was just thinking. If you calculate the pairing, this doesn't help you.
Yeah, now that's right. So the A infinity enter in this factor. However, here the important thing is how close these two cycles are, or these values are. And it turns out that you have a factor, and the factor which tells you that they are very close involve only the derivations on the.
So the prefactor is A0 minus A0 prime as well. I mean, you must have a difference between.
No, the factor will be certainly involve A infinity values of all of them.
So what have we gained?
Well, what we gain is that we can have two co-cycles close to each other, and these A's can be they can be quite far apart, but they will be close to each other as long as they are smooth. As long as the derivations are close to one another.
Mm-hmm.
Well, in any case, this one saves us when you define the index, then you ask, okay, is the index continuous with respect to the formations? It will not be, and the projection doesn't depend, jumps discontinuously in this norm, an infinity norm, but that's irrelevant as long as this factor remains bounded, because this one varies continuously. As you, for example, change the Fermi level. Okay.
Okay, Emil, I think I'll drop out. It's getting a bit late here.
Okay.
So
everybody, and maybe.
Thanks for the talk.
Thank you. Maybe we keep all these issues alive until the very last day.
Yeah, that's right.
We have because then we'll have more more context and things.
Okay, take care for now.
Bye.
Can I ask a question?
Yeah.
I was wondering, when I also think about whether it suffices to look at the algebra, I was wondering if you remember the work of Panatti and company about non-vanishing of Chern numbers and localization or not, also non-existence of localized Wannier functions. Is there anything one could also push towards the bulk boundary correspondence? And so then the problem of delocalization at the boundary could be somehow related to that?
Uh-huh.
So I don't know whether there is something pushed already to the bulk boundary correspondence in this framework. Do you know something about this?
No, but So let's see, we have the formalism by Bram and Guo-Chan.
Are they still listening?
No, their statement is that there is to find a localized linear functions, you need a finitely generated module, no?
Yes.
Project.
Just a second, I was not at my seat.
Okay.
So Johannes was asking if you start with a linear function problem, which you, Bram, and Guo-Chan studied, and what will happen if you push that to the boundary, to the bulk boundary correspondence?
That's a good question. What I can confirm, as Guo-Chan also did, is that you start from some FGP there.
Sounds sexy, FGP.
So you have the
no one knows the answer to this.
projective, and then that module is a Kasparov cycle or not?
Well, it's a finitely generated projective.
So it is. So you can.
As such, it is a very simple Kasparov.
So then you multiply it with the extension.
Yeah, this you could do.
And you should get a statement on the boundary.
It's not that simple, I would think, because it's then you're in a completely different setting.
But at least you will be able to produce a projective module on the boundary.
No, because the module that represents the extension
is
generated and has an operator and all that.
Operator.
So you really, and there is some stuff to go through there if this is possible at all.
Okay, now the other question is why not use this criterion in the interacting case? So you get a CAR algebra over there, and you say define a topological phase, the one which you cannot define a projective module over what?
I'm not sure if I understand your question now.
So can you push it into the context of the CAR algebra?
Well, there should be. I mean, I think. Yeah, I would have to look again, but some of the statements that Chris and I wrote down are fairly general. But you would have to start again from, if you have a natural projective module there, or okay, our algebra seems to be non-unital, so you would have.
But we would not expect this, right? We would rather expect the contrary, because we would expect that that we do not have localized 1A bases on the boundary, right?
But then you have also the other statement. Maybe if you do have one in the bulk, then you'll have one on the edge.
We don't expect it, right?
In other words, if the state is trivial in the bulk, then also the edge should be trivial.
There's a key difficulty here, which is that the one-year functions are, even though they look discrete, sort of like a regular representation of some discrete group, they're embedded in the continuum. So once you have these operators for which certain spectral subspaces define the subspace in which you want your one-year functions to span them, if you have a space with boundary, then the boundary conditions come into play quite strongly. So it's not such a direct question. So what you want from the one-year basis. So it's quite involved, I would say, to even formulate what you mean by a localized one-year basis for Hamiltonian I guess you want this to be some sort of differential operator. I mean, the Hamiltonians actually come from continuum models, and the whole point of this exercise is actually to justify the tight binding picture. So there are actually quite a few steps in order to get to even a formulation of the boundary correspondence in a precise sense in terms of one-year functions. So not just in the decay of the one-year functions, but especially in the case where you have these gapless H states, how you even formulate the problem of having a one-year basis, what it even means. Nevertheless, people have studied situations where rather unrealistic situations where you can you try to get these one-year functions with extremely good decay. And in fact, this is from a paper of Reed some time ago, using algebraic K-theory methods. In that case, then you really can just truncate violently and impose a Dirichlet boundary condition, for example. And then you can automatically get a one-year basis just by restriction. But otherwise, it's not a simple matter of restriction. You have to look at the operator from which the one-year basis is associated. Yeah, hopefully this makes a bit of sense. It's a little bit. It's not a very precise comment.
Does this work you mentioned involve? You said algebraic K-theory method, so it doesn't involve other groups than K0?
No, I don't think so. I think there was a K1 group somewhere. Yeah.
Okay, that's also
yeah. But yeah. So I think it just came from Laurent polynomials. Yeah, sort of ring. So it's not completed to a C-star algebra or anything. But there you can still make sense of the K-theory groups. Of course, these such functions will have tails which decay even faster than the inverse Fourier transform of a continuous function. But they are very unrealistic in the sense that given a differential operator, so Schrodinger type operator, you almost always, I think it's generally impossible to get one-year functions that have that sort of property. And people at best try to get exponential decay, which is already quite difficult.
Maybe I throw one more thing with this almost frantic quest of formulating what this topology will enter in this interacting system, CAR algebras. One aspect that occurred to me was that if you have a state and you want to compare, when you want to compare two states, then the natural one way to quantify the difference between the two is to look at the left ideal, which is the null space of the two states. Now these are monsters, so they are countable but not projective in any way. However, I think if you look at you can somehow still manage to look at differences between such left ideals, or at least to say some topological statement about them. I'm not sure how.
Are you thinking of what other people discuss where they classify the ground states of these sort of interacting systems, and rather than the Hamiltonians themselves? So I'm a little bit confused about the framework that you're thinking of.
So what I just said.
Yes.
Well, I can give you a very simple example. So you take a Hamiltonian, a local Hamiltonian, and on the CAR algebra, let's say you have just a derivation, which is everybody is comfortable with the derivation over the CR algebra. In the CR algebra, you have several circle actions. And when you apply these circle actions on, you can get a family of derivations, actually. And this family of derivation gives you a family of states. Now, you would like to cook up an invariant out of this family of states, which just come from these circle actions. And being circle actions, you can be sure, for example, the spectrum of the Hamiltonian is preserved, the gap is preserved, all these things are preserved, but the state itself moves. Can you cook up a topological invariant associated to this class? And I managed, in my picture, this was just a family of left ideals, which are indexed by the circle. Can we associate a topological invariant for this context? And what kind of assumptions you have to put on these left ideals? Of course, if the left ideals will be projective, then I know immediately how to approach them, but being only countable,
I don't really understand what the left ideals could tell you that the states don't already tell you, because if you divide by the left, if it's in pure state, if you divide by the left ideal, of course you get the Hilbert space. That's Caddison's theorem. So yeah. It seems to me that to talk about the left ideal is just a complicated way of talking about the state. Do you know what I mean? It's not like it's extra structure. It's
the problem is that here the Hilbert space moves, so it's difficult to deal. You like to embed everything in the same gluing structure, and the gluing structure is the CAR algebra, and for sure these left ideals are glued together by at least in a same structure, as opposed to these GNS representations, which are one disconnected from the other. If you,
I mean, are they disconnected? They're all built in the same way. An element of A gives an element of all of these representations of the CAR algebra, gives a vector in all of these Hilbert space representations. That's the GNS construction. So that there is this family of GNS representations comes with a canonical collection of sections that you could even call them algebraic. You know, the canonical sections just given by elements of A. So I don't know. To me, it's kind of upsetting to think about the left ideal. It's something, and you divide the C-star algebra by it, and you get a Hilbert space. That seems very complicated. On the other hand, if you just look at a state, isn't that the purpose of states? They're just easy to think about.
Well, my hope is that okay, that will give me at least the right or left module, the right module which I could feed it into a Kasparov cycle.
Okay.
Yeah, but you really need extra information then, right?
Extra information to.
I mean, it's in interesting cases almost surely infinitely generated, and yeah. So you really need something else.
So Nigel, but let's say these modules will be well behaved. Mm-hmm. So I can give you example. Let's say the algebra of generated by one unitary operator, and then we twist. Can I? I generate a Hamiltonian out of this, I mean, just a Hermitian element, and then I twist this unitary by a phase, and I get a family of Hamiltonians out of this, and they depend on a parameter on theta. Suppose this Hamiltonian has a gap, and I define a state using the gap projection. So I got a family of states parameterized by this theta. How will you define the winding number in this case using the state? This dimension.
So I'm trying to understand what you're saying. So you have actually a family of Hamiltonians, you said, and the gap is supposed to be the same in each of them. I didn't, or can the gap move?
If it's a circle action, then you guarantee that the spectrum remains the same because they are just.
So the Hamiltonian is just the generator of a circle.
No, the Hamiltonian is a self-adjoint element from the algebra. Yes. So it's just a few powers of linear combinations of powers of U, and suppose it has a gap. Now you take U and you replace U by lambda times U, where lambda is from the circle, and you will see that Hamiltonian changes. The spectrum doesn't change, but the Hamiltonian changes, and the projection, particularly the projection in the changes.
Oh, okay, I guess okay, fair enough.
So now you have a, it's very easy. You add a bundle of right modules if you like, but now, and that's, I can see these modules precisely from the null space of the state.
Okay. But you could also see them from the GNS Hilbert spaces, and but you ask, are you asking for another definition of something that you've already managed to do, which is to attach some winding number to this, or are you asking how to get some winding number out of this?
Okay, so no, how will you go with the GNS representations?
Well, I take this Hamiltonian, I take the spectral projection in the GNS representation. Now I have a Hilbert subspace. So I have a bundle of Hilbert spaces over the circle, Hilbert subspaces over the circle. Of course, by itself, it's not much, and it doesn't have any invariance, which is why I was asking, what else, what am I supposed to do?
Okay, so now we have this, but you have an entire Hilbert space.
Well, two, in fact, not only a Hilbert space, which is the GNS Hilbert space, but some subspace, which comes from the spectral projection. But still, I don't know what, I mean, I don't know how to get a numerical invariant out of that. I don't think you've told me enough. Or I haven't understood enough, that's for sure.
Well, but this subspace is still infinite. Now you go around, let's say, about the base space, and you have this. Is that enough to cook an invariant?
No, I mean, not with what I understand. No, you need more. And a bit like Bram was saying, you need something more, and I don't know what it would be.
Yeah, so you need.
I think a little bit about the setting Emil was thinking about, but you need to feed in some extra information.
Yeah.
Can the Fredholm, the F operator, save the day?
Something like that, yeah.
Yeah, but you need to cook it up.
Emil, I don't know if it's the same situation you're thinking of, but very often in superconductivity, you have some reference Fock space for this CAR algebra over, say, an infinite lattice. And and then you do some variation in your Hamiltonian, and you follow the ground state, or indeed the projection below certain gaps in this many-body Hamiltonian. And typically what's happening is you have some Pogorelov transformation, which actually can, and is implementable inside this Fock space. Then of course you can follow a loop of this Pogorelov transformation. These form some orthogonal group that has the same homotopy type as the bot orthogonal group. And so there are interesting loops in there, for example, and you can calculate how the eigenstates, I guess, evolve around this loop within this initial Fock space representation. So there are some things you can cook up, but I don't know if it's a situation that you're thinking of. Does it make some sense to you?
Except that in our case, there are an infinite number of states involved at each point, for each parameter, for each value of the parameter.
There are an infinite number of states at each point.
So the projections in the
right
are not finite rank.
Yes, yeah, that's right. They're not finite rank, but you can nevertheless so this orthogonal group that I'm talking about actually is taking place in an infinite dimensional Hilbert space. Yeah. So actually, this is what Chris was talking about as well. The implementability of this Pogorelov transformation inside one particular Fock space depends on having a difference which is within, for example, this Hilbert-Schmidt class.
Yeah, the Hilbert, but in that case, for his, so he lands in K1 of that algebra, I guess. So then the group minus the identity always lands in the
yes, yeah. So it's sort of a restricted orthogonal group.
Maybe that's one should look at.
In fact, this is the particularly of some use because it is the homotopy groups are known for those groups, and it's not contractible unlike the full orthogonal group. So this one is there's some hope, and I think it's actually relevant to the one-dimensional infinite Kitaev chain. But maybe you can discuss this another time because it's a bit big.
Yeah, we're still live. Okay, so don't forget tomorrow it's 10 a.m., not 11. So 3 speakers. Good, so I'll see you then tomorrow.